Sure.
Yeah.
So anyway, um, oh,
Are you?
yeah, go ahead.
Oh, no, no. I was just about to ask you, are you in London at the moment?
Yes, I'm in
Ah,
London.
okay.
Yeah, I don't know when to go back to uni
Ah,
because like I don't know what's open and stuff. I sent
uh, yeah, okay. So, do you? Mhm.
all right. Okay, so let's get started then. All right. So hello and welcome to my presentation on a novel approach to non-adiabatic transitions in quantum systems. So let's get started. Suppose we've got an electron. Now, quantum mechanics says a couple of interesting things about this electron. Firstly, it can only occupy discrete energy levels. So this right here is an energy level diagram. We've effectively got a ladder here. And each rung of this ladder, each horizontal line, effectively tells you an allowed value of energy. So what's very different from classical mechanics is that an electron is allowed to have, say, this particular value of energy or this particular value of energy, but not anything in between. Another stark contrast with classical physics is that if you were to make a measurement for the energy, there is no way for you to predict beforehand what energy level you will find the electron in. The best you can do is talk in terms of probabilities. So the best you can do is say that there's this much probability, this much chance you'll find it in this state, this much chance in this state, and so on and so forth. So now in my project, we focus on only two energy levels. So here we had effectively infinitely many. Just focus on two, that'll do. Say I put an electron in the upper energy level. So somehow I know with 100% certainty that my electron is in the upper energy level. Maybe I made an experiment and I measured it already. Now, there's an important result in quantum mechanics called the adiabatic theorem, which states that provided the total energy of your system, the Hamiltonian effectively, doesn't change, provided that's true, if your electron is in one of the energy levels, then it's going to remain in that energy level forever. No transitions would happen and life would be pretty boring. However, this is not the case if you make your energy levels change in time. So in our experiment, at around t equals 0, the middle of our experiment, say we make our energy levels wobble around a little bit, and then the wobbling dies down. Then there's going to be a small but non-zero probability that the electron will jump to this lower energy level right here. We can represent how much this wobbling happens, the extent of this wobbling, by a positive number epsilon. Now, my project asks, how does this probability depend on epsilon? Of course, the smaller epsilon is, the smaller wobbling you've got, and the smaller the probability is going to be. But let's try and find a more precise relationship and quantitatively figure out the probability. So now I'm going to jump into some technical details. I hope that's okay with you. It's okay if many of these concepts look very unfamiliar, and if you don't feel like you understand most of it. I just want to give you, as it were, a whistle-stop tour through the theory. I just want to give you a taste of the results that we've discovered in our project. So traditionally, what would you do? You'd write down what's known as the Schrodinger equation right here and try and solve for psi of t. This right here is a function. It's known as the wave function. And this h of t is a matrix. Matrix is just a fancy word for a bunch of numbers in an array. This h of t, the Hamiltonian, loosely speaking, represents the energy of our system, our total energy. Now, you're trying to solve, just like any old equation, for psi of t. What is psi of t? So this, effectively, this is what represents the state of your system, of your two-level system. Now, this matrix H has got certain what are known as energy eigenvalues, so plus a half and minus a half. And each of these eigenvalues have got corresponding eigenstates, phi plus, phi minus. Why am I telling you about all of this? Well, phi plus and phi minus, they've got special meaning. So as I said, the best you can do in quantum mechanics is represent your system with a wave function. Now, if your electron is in the upper energy state with 100% certainty, then phi plus and your wave function coincide, right? The energy, the eigenstate corresponding to plus a half is phi plus. Psi of t will be equal to that. If you're in the lower energy eigenstate, then psi of t will be phi minus. Now again, as I said, in general, you can't figure out with absolute certainty which energy level you will be in. So in general, your wave function will be a mix of the two, right? So this corresponds to maybe a probability plus a half and plus a half being in either energy levels. So in general, psi of t will be a combination of phi minus and phi plus, and the coefficients here, these numbers, roughly speaking, tell you about what the associated probabilities are. Now let's talk about our approach. We took quite a different approach in the project. Now, so the traditional approach, just to finish off the traditional approach, it uses the concepts that we've discussed already and provides a long method only to give an approximate answer. So we took a different approach. We looked at what are known as density matrices. So instead of a wave function, you can describe your quantum system equally well by a 2x2 matrix, right? 2x2 matrix, which is known as a density matrix. And it's got certain special properties that we exploit in the project. So here, as an example, so before we described the upper energy level with this wave function, now the corresponding density matrix would be this guy right here, 0, 0, 1. If you're in the lower energy state, then pi of t, which is the density matrix representing the system, would be 1, 0, 0. By the way, this pi is just a Greek letter. It's nothing to do with the 3.14159 number. Okay, so up to this point, we said that traditionally you describe the system of the electron in the two energy levels by a wave function, but instead you can describe it by a matrix, which is known as the density matrix. And this density matrix has got certain properties to it. Notice if I add up the diagonal elements, I get 1. That's, for example, one of the properties that it must have. Now, one discovery we made, an exciting discovery, is that you can equivalently describe a density matrix at a given moment in time by a point in regular three-dimensional space. So for each moment of time, you get a different point in three-dimensional space, which traces out effectively a path. So this might be, it might look something like this. Okay, we call them trajectories. Now, the question is, what is this particular path? Because if you can figure out what the path is, what the x, y, and z coordinates are as a function of time, then you can effectively solve the problem that we are trying to analyze. Now, a second important discovery we made is that the path must be on the unit sphere. Okay, this describes what the unit sphere is. And also, so points on this unit sphere correspond to different states that the two-level system can be in, right? So the North Pole, for instance, turns out, corresponds to the electron sitting in the upper energy level. And notice, I said that at the start, at t equals minus infinity, my electron is sitting in the upper energy level. So we know that any trajectory must start at the North Pole. So just to summarize this, 4 different ways of seeing this. So the electron is in the upper energy level with 100% probability. You can think of this as having this wave function phi plus. Or you can think of it as having this density matrix, or you can represent it by just simply this north pole. And likewise, lower energy state, this density matrix, this wave function, and the south pole. So north pole corresponds to the electron being up here, south pole corresponds it to being down there, but in general it's going to be in the mix of the two. So you're going to find yourself somewhere on this sphere. Now finally, our question was, what was the probability? Well, it turns out that we discovered this simple formula, and that gives you the probability at a time t. And then we derived, so we need to figure out what x, y, and z are, what the coordinates are. We derived what are known as differential equations. And if you can solve this, then you basically get x, y, and z. So what we did is we used MATLAB, a software package, to numerically solve these functions. And this is what it looks like here. So notice how as epsilon gets smaller, the path gets tighter and tighter, and it gets closer and closer to the North Pole. And that's sort of intuitive if you think about the probabilities. And then here we've plotted the probability as a function of time. Notice that the peak happens at t equals 0, and it gets smaller and smaller as epsilon gets smaller. It makes sense that this happens at t equals 0 because that's where we're actually shaking the system. And then the final important graph is that we also plotted the probability in terms of epsilon, and we got this shape. And what's really nice is that the paper that we based our research on, that we started from, predicted basically this type of shape to our curve. And if we plot the logarithm against logarithm, it's even more, it confirms it even stronger. So just to summarize, instead of this complicated traditional approach known as the superadiabatic basis approach, we derived a differential equation that we saw here. We derived this. And then what's really nice is that there is a vast theory, a rich and vast theory to analyze differential equations. And so this is nothing but the end. This is the starting point, and you can there's a lot of interesting research that you can take forward from this point. And then the final question is, what if you have 3 levels or more? Turns out that really interesting effects might happen. So thank you for your attention. Are there any questions?
All right, great job, mate.
Okay.
That was really cool. Like you went out like 1 to 2 minutes
Okay.
out of time, but okay, yeah. So yeah, that was quite a nice talk. One question out of curiosity. I mean, probably you will not get asked such questions, but it's like it's my question, like out of curiosity. Like, if you were to study, for example, 3 states, as you mentioned at the end, you would have like the psi of t would be like a vector, a column vector with 3 entries, right?
Yes.
Okay.
Yeah, your Hamiltonian would be 3 by 3. You have 3 orthogonal eigenstates, orthogonal normalized eigenstates, and so you'd have a vector in C3 at each point in time. That would be a frozen wave function. And then your density matrix, I suppose, would also be 3 by 3.
Okay, because that is where I would get like I would like to ask like right after, like what happens to the density matrices, like, because the density matrices are defined with the help of Pauli matrices. So if you had, and the Pauli matrices are 2 by 2, so what would happen in that case?
That's actually a really good question. I really like that. But the thing is that they're not really defined with the help of Pauli matrices. We've defined it already, and then we said that we defined the coordinates in terms of the Pauli matrices. Right? We said that the Pauli matrices form a convenient basis for traceless Hermitian matrices 2 by 2. So that gives you X, Y, and Z. So, you'd have to, that bit you'd have to substitute it for something else.
Okay, I see.
Yeah, that is definitely very interesting.
Yeah, that makes sense.
Yeah.
Yeah. All right. Yeah.
All right.
Yeah.
Then. Well, yeah.
That was a nice job. I mean, you are gonna be competitive tomorrow, as I guess.
I hope so.
Yeah.
Yeah. I hope. Yeah. Just the final thing is to try and cut it down to 10 minutes. I'll email them and ask if it's if they allow you to go over a little bit. It's not it's probably fine if you go over. I'd imagine probably even for the prize, like ideally you'd want to do it in 10 minutes, but I'd imagine they're looking for quality,
Yeah, well, if you go out like some seconds, then probably they won't. But if you go more than a minute, I mean, I would
Yeah.
strongly advise you don't go out. I mean, if don't go out more than a minute. So
Yeah,
yeah,
I'll rewatch this and see where I'm like. I think at the start I was a bit like slow, slightly slow this time.
yeah, and
Yeah.
stop a bit over there. Yeah, I think at that point, like you talked a bit like too much. I mean, you explained that it's some maths, and you explained that they want to get that you want to give them the idea, but
Right,
yeah.
right. Yeah, true. I can just cut that off this a bit. Yeah.
Yeah, well,
That's true.
yeah, not too much, but you can cut some seconds from there as well.
That's true. That's true.
Yeah.
Yeah, I can rerun it without that bit.
Mhm. Okay.
Or I can just write what I said on the slide,
Mhm.
Yeah, anyway.
Yes.
Yes, that's good. Anywhere else that was starting to get a bit slow here-ish as well. Yeah. Anyway, I'll cut it down and see what I can do. Yeah.
Mhm.
Well.
Yeah, it might be worth it, like the handwritten notes. If you write it on latex, it might be worth it.
Which one?
Like yeah, go up slowly. Yeah, that one.
That one.
Yeah, I mean, yeah, yeah, that's up to you. I mean, it's quite nice either way, but I would prefer to type them. Ideally, I would prefer like if to have it all typed by computer, all typed by computer. But yeah,
Fair enough. I
I
mean,
mean
the
that's
thing
up to
is,
you.
yeah, the thing is, this is handwritten, this is handwritten, this is
Yeah,
handwritten, and then this is handwritten. So it's like, I guess at least it follows a
yeah.
little bit of a narrative with this being handwritten as well. Like you can associate
Okay, yeah,
this
yeah,
story,
fair enough.
maybe. I don't know.
Yeah.
But yeah, thanks. That is a good point. I think I
Mhm.
might keep it handwritten though.
Yeah. I mean, yeah, it's not a big problem. It might not be a problem at
Also, it
all.
looks like I put more effort in it as well. I don't know.
I mean, if someone can see it clearly, then it will be all right. I mean, if there are some details, but yeah, I mean,
Yeah,
it might not be a problem at all. So yeah,
yeah.
if you feel like it, you can leave it like there.
True. Yeah. So maybe the handwriting. Yeah. Okay. Thanks. That's a good point. Anyway. Um. Yeah. So I'll carry on and carry on with this.
Uh,
Yeah. Thank you very much for your help, mate.
oh, that's all right. I enjoy it, like seeing this stuff, because I educate myself on things kind of related to what I had been doing and related to what I'm doing right now. So I enjoy it, and I would be
Yeah.
happy to have this conversation again in the future.
Brilliant. Yeah.
Yeah.
Um. Yeah. Anyway, I'll talk to you soon. Then.
All right. Yeah. I mean, yeah. Text me tomorrow, like tell me how it went.
Sure.
All
Great.
right.
Fantastic. All right. Take care, man. Take care of
Good
yourself.
luck, mate. Good luck tomorrow.
Thank you so much. And
That's all right.
yeah, I'm still reading your appraisal thing.
Ah,
That's very interesting.
okay. I mean, yeah.
Thanks for sending that. Thanks for sending your presentation as well.
No, that's all right. No problem at all.
Brilliant. And
All
yeah,
right.
see you in Lancaster soonish, I hope.
Yeah, I hope so too.
All right. See ya.
Good luck tomorrow.
Bye.